this is the course Visualization Basics with ParaView. If that's not what you're expecting, you're in the wrong meeting, I'm afraid. And I'm Joanna Leng, and I'm a EPSRC, which is the Engineering and Physical Science Research Council in the UK. And I'm a research software engineering fellow working on novel sorts of imaging using developing software for that. So this is a ParaView, and visualization is a very vast topic, going from human perception to supercomputers to graphics hardware and simulation. So lots and lots of topics. So my key aim is to give you the ability and the vocabulary to be able to do good key searches and troubleshoot your visualization and ParaView issues. And this is why I've provided reference materials, which are your crib sheets. So they have a lot of the keywords in them, quick key moves and things like that, which are useful. So do keep them as reference materials after the course to help you actually do that. So this is the contents of the course. So we've got a brief history of visualization, then the visualization pipeline, which is the key thing to understand in terms of computerized visualization. My view is that visualization is distributed computing, and that's important to you to understand the graphical user interface and how you could use it with a supercomputer. Then we've got some exercises and a break, so you can have a rest and you can ask questions. And then we've got something on color. Color is the quickest way to massively alter your visualizations, and it happens on the graphics hardware normally, so it's very quick to implement. Then we've got a little bit on visualization data structures, visualization design, and how you can use that to optimize your visualization pipeline. And that's all sort of useful stuff to know if you're going to use Python to program in ParaView, which is, of course, will release a lot more power for what you're doing. So does anyone know what an RSE is? So it stands for Research Software Engineer. And on the new Wikipedia page, it says that it uses research software engineering. It's the use of software engineering practices in research applications. So that's bringing computer science in a way to all research applications. The term started to be used in the United Kingdom in 2012 when it was needed to define the type of software development needed in research. My view is that there's a slightly different process needed for research software development, partly because, well, the way I do it, I work very closely with the scientists right at the beginning of the research process, so it needs to be very flexible. And this focuses on reproducibility, reusability and accuracy of the data analysis and applications catered for research. So this comes to the open research sort of focus and reproducibility issues as well. There are many large simulations on HPC which you just can't repeat. So people publish results on them, but no one else can ever repeat them. So there can be issues there. So this is there's a milestones of visualization project which looked at all the different things, and this is the oldest one that they thought was a visualization, which isn't cave painting. They've cut out cave painting, but the oldest map is 6,200 BC. That's 8,000 years ago. So I think that predates written languages, really. I don't know, I'm not an expert, but it's a fundamental way we communicate. It's a very useful way of communicating, and the visual issues are very good at doing that. So, so are computers necessary to visualize? Well, most people, when you say visualization, they actually think there's a computer there. It's a bias, probably an unconscious bias that we've got. I can't think of any other words for that. But visualizations predate the existence of computers by, as we see, 8,000 years, and probably started before text. And they're a very fundamental means of communication, and they store information as well. So it's a good way of condensing down information to store it and communicate it and present it to other people. And if you look at the milestones of visualization projects, which I quite like looking at, you can see jumps in visualization are connected to developments in art and other forms of communication. So when the printing press was produced, visualization had a massive boost and a lot of more techniques were developed. And when paper was developed as well. So the milestones in the history of thematic cartography, statistical graphics and data visualization, if you're interested in that side of it, I recommend having a quick look, and you can see the invention of computers, massive boost in visualization techniques that have arrived. So here is some questions, and in a room I might have a bit of a discussion, but these are just some of the things that you consider. Are cave paintings art, or are they visualization? Is art visualization, or is it is visualization art? So when I went for job interviews about 12 years ago, everyone kept on calling me an artist, which I'm not. I'm a visualizer. But the two are linked, and it can be quite nice working with artists with your work as well, to get extra creativity in what you're doing and draw the research questions out in new ways. So I think visualization is a way of exploring, storing, and I'm going to have to move your images, and understanding information. It comes from a need to create, learn, store and communicate information, and it predates all civilized forms of communication. And the quality of visualization reflects the technology of the time in which it was created, the cultural practices, which is important in using the data and information. I emphasize cultural practices because there's a group of visualizers who see visualization as perceptual psychology, an area of perceptual psychology. And I don't think it's always that. And I talk about that slightly later on when we talk about colour blindness. So cultural influences in visualization. Edward Tufte has a particular view, and he has beautiful books which are very expensive. You can have a look at them. And he looks back at the social, well, he's an economist at one of the important universities in the US, and he looks at what the scientific need was there and what the social need was there for the development of different types of visualization. So yeah, visualization predates science, and what the meaning of science is has changed in the last 200 years as well. So you can, there's a view that scientific visualization and information visualization were the two paradigms of visualization, and things don't quite work like that, but that was a viewpoint. So we'll talk about that a little bit later on as well. So he views visualization as the appropriate analysis and appropriate presentation of information. So it's very much about the presentation of information. So improving user experience. So this is more about perceptual psychology. So Colin Ware's done some great books as well, and he wanted to be an artist, and then he became a visualizer, and he sees visualization as an area of perceptual psychology, and a lot of usability tests are based on perceptual psychology, and they time how quickly you are to do something. There used to be a view that if good usability will mean that your visualization work will be adopted, and that's not quite the case. There are more social interactions going on. And as a dyslexic, I say, you know, there's not enough known about perception and the brain to make this method robust. So there are things that other people will be able to handle, but my perception won't work. So I'm a bit skeptical of that technique. So academic disciplines are a relatively new concept and have all grown with their own ways of presenting data. That's a sociological issue. And we use the word culturally, which shows us that. So culturally, visualization has been a full academic discipline probably since the 1980s, 1990s. So it's about 30 years. And it has similar difficulties to statistics, and the RSE community has the same sort of problem. It's a practitioner area rather than pure science. So it's not very theoretical, but most disciplines use computerized visualization in the form of ParaView or other tools. The problem is doing it well. How do you do it well? And how do you know all the functionality of the system? Because there's a lot of functionality. Right, so this is an overview of the topics in visualization. We've got hardware on the left. I'm building up a diagram as we go. And then we've got the visualization system. So this is the software that is very related to the hardware, particularly if you've got large data or large virtual environments or virtual reality environments that you want to connect it to. Then you've got applied visualization, where you work with the scientists. Most of what you guys are doing is applied visualization. And then you've got the generic techniques, which are a kind of halfway between the two: isosurfaces, or as ParaView calls it, contouring. So computing shape, statistics and image processing are in the applied side. Mathematics, usability in virtual environments cover the whole area. And here we've got parallel programming, meta computing and computational science, which fit in there. So that's an overview of how it all fits together as a discipline, going from the pure to the applied. And then we've got the art and graphic stuff, which helps you understand how to present the final data. So there used to be a big rift in the visualization community about what scientific visualization is versus information visualization. And when visualization first started, it was really linked to big engineering problems run on supercomputers. And that's how it started. So it's 3D problems. And that was what was characterized as a scientific problem, the fact that it was 3D. But that doesn't really work. There's lots of science that's done with 2D or with data spreadsheets and things like that. Scientific visualization was really the first computerized visualization, and the name's kind of stuck, but it doesn't necessarily work very well. And it really relates to 2D or 3D simulation or scan data that we've got there. And this is the area that ParaView is really fitting into. It's looking at the 2D or 3D simulation data. It has issues with working with scan data. There's a product called TomVis, which actually might work better with scan data, but you have to convert the scan data, if it's stored in slices, into a block of data, which I was going to put in as an exercise for today, but I haven't. So I apologize to the people who are using scan data, medical scan data. And information visualization was developed after scientific visualization, probably 10 to 15 years. And this was the social scientists who had databases and spreadsheets. So they didn't want to call it social science visualization. They called it information visualization. But you can actually transform data that's 3D into databases, and databases, you can project them onto maps, which are 2D or 3D. So it's a lot more complex, but this is the old naming system that was there. And so you'll find a lot of reference stuff that fits that. So scientific visualization was based on the scientific investigation model, which is a cyclical event where you get data, you look at it, you create a hypothesis, you collect more data, you run simulations or analysis on that, then you'll visualize that, you'll look at the results, you'll get more insight, and then you'll do a new hypothesis. Of course, the you can interact with the visualization system. So there's a much quicker interaction there. And the visualization pipeline is really the computerized data flow or workflow of a computerized visualization system. So you've got reality. The scientist looks at reality using experiments or equipment like the Hubble telescope to look out to space, or microscopes. You've got the numerical methods experts who will change that into a computer representation of reality. And then that would be very difficult to look at as if you looked at it in binary form or as printed data structures. So we really need to turn that into images, which are much quicker and easier to look at. And that's piped to a display device. So you have the visualizer who's creating these ways of presenting the data. But of course, the pipeline is all connected to the hardware that you use. And it has certain key terms, which is why I've written this out. So if you're looking through the ParaView documentation or otherwise, this is the area that you'll look. So at the top of the pipeline, we've got the hardware, and at the bottom, we've got the processes. So the computer representation, the numerical methods are run on a computer, like a supercomputer or your desktop CPU. The images generally are much quicker when they're created in hardware. So they're created on the graphics card, and then the graphics card sends it out to the screen or whatever your display device is. And the processes that are involved here, so the numerical methods relate to simulations or analysis, which are key terms that you need to look for. And rendering is an important term to understand, that that's how you turn your data set into an image. So that's a very key term to know for looking up terms. And in ParaView, they have something called the render view, which is where you see the rendered actions. So ParaView is developed in particular for in situ visualization, and this is the Catalyst part of ParaView. I'd hope that we could get Catalyst activity in ParaView installed on Bead, but that wasn't possible. But it's something that might happen in the future. This is also being used for large data. In situ visualization is being used for large data, which isn't 3D. You know, it fits the information visualization area, and Jonathan won't talk about that on Thursday, but GlueVis is enabled to do this as well. So this is relevant to information visualization systems as well these days, because the cloud is so pervasive for the storage of data. So so if a visualization is too slow, you can reduce the size of the data, you can reduce the computational cost of the techniques that you've got there. You could put high performance graphics in there. You could actually even move some of the visualization back into the simulation and run a isosurfacing in your simulation if that was relevant. And complex simulations execute slowly. You can use remote computers, and you can use Catalyst to monitor and check that your simulation is running and doing the right thing, and look at the time sets as it progresses. And if you can get interactive time on a supercomputer, which is very difficult unless you work in the big American labs, they tend to do this more commonly. You can request it, but you could run a visualization system if you're at the same time, and then you could interact with some of the parameters that guide your simulation and see how it works. So if it's working in real time, if you've got a simulation that's working in real time and it's connected to a visualization system, that's all going to run on your desktop, and you can probably output to some sort of graphics pipe from your simulation. If it's interactive, it's a little bit longer, but steering is when you're running a simulation for about a day. That's when it becomes relevant. So this is where I try to show that visualization is distributed computing, and this is so used in scientific and information visualization here these days. So you can, most of you, if you're using Bead, you might be running them on Bead, which is a supercomputer, and it will speed up a slow simulation, so it'll make it run a lot faster, and it might even make some of the simulations that weren't possible to run on your laptop possible. At the end of the simulation, you could save the data and then pass it to your laptop, or you could stream it directly to your laptop and just read in the input data and visualize that. And then at the end, you can steer it, the simulation, to alter the computer representation of reality, but you always need to go back to reality images or other data to check that the simulation is correct. And there used to be an area called comparative visualization, which would allow you to compare real images of an experiment with a simulation of the same thing to see how close to reality your simulation was. So this is another way you could have distribute your visualization across systems. And here you're running some of the visualization and the simulation on a supercomputer, and then to your desktop you're passing the OpenGL or compressed images. So you could render in hard software on the supercomputer and pass a stream of images back down to your computer if the data is very large. And there we go. So, and then this is the final one. When we're using virtual environments, we might have multiple hardware for the haptics, the screen, the sounds, and then we're passing all of those out through the visualization system. So I think ParaView will work with virtual environments, and it will give you some haptics out. It used to, a long time ago, I used it for that. So you can separate it out there, and you can combine these models in various ways. So it is relevant to the GUI, what I was talking about there, but that's in a couple of slides. So I'm going to give you an overview of the ParaView GUI here in slides. I'm not going to do it as a cutaway to ParaView, which I sometimes do in person meetings. I've created 2 crib sheets, one for ParaView just plain and one for Python with ParaView. And what I've done, there are quite a few quirks in ParaView and issues around where the user interface is. I've tried to put them on the crib sheet so that you can keep that with you at a later date and find out information. It gives you information on quick key shortcuts. It gives all the key terms, what's in the names of all the menus are laid out so you can find things more quickly. And it links to documentation and other materials to help you with troubleshooting, because that's one of the things you'll need to do. So the ParaView visualization pipeline uses a different terminology to the one that we had before in the other pipeline. It calls all the modules filters. So you'll be looking for filtering. Sometimes it will call mapping. The rendering is the render view. And because actually this is called the data flow paradigm, where you pour the data in the top and it flows down like a waterfall to the bottom, and your display device is where you see it. But ParaView doesn't work that way because it works with large data. It likes to know it has space for all the data before the module will read in the data. So in actual fact, it has a pull capacity. So it will work out what the memory it needs for all of the pipeline, and then it will go and call for the data from each one. So it has a pull rather than a push paradigm. And so there's this button, apply changes. And this apply changes button is very important to understand, because a lot of people forget it's there. And then they go, I've changed everything, but ParaView never changes. I don't understand it. And it's because you've got to press a button, apply the change or apply each time you change a parameter that occurs on the CPU. You don't have to do that if it occurs on the graphics card, or you can press this button if you've got small data, which appears at the top, which will just automatically apply the changes. And that's one of the big things that a lot of people forget about with ParaView, and it puts a lot of people off. So ParaView is an area of modular visualization environments, which is, they're not termed that anymore, but instead of calling the filters, I call them modules. And a module can create a filtering, a mapping function, or it can create a sphere as well. So in my terminology, that's what I'm using it. And it's important because users can extend the functionality, which is what Python will allow you to do. The visualization is it analyzes data and presents it visually appealing form, which adds meaning and interaction often with it as well. And then it's an environment. So it's got libraries of these modules. So you can select libraries and fit them together into a pipeline. It's got a visual programming area, which is the pipeline. There's a pipeline viewer in ParaView, which will allow you to see how the data flows through the system. And then it's got the graphics scene. The graphics scene is rendered on the graphics hardware. So you'll have, I think it's in the next slide, we've got a little bit here. So this is the graphics scene. You can interact with objects with your mouse in the graphics scene. You've got the visualization pipeline viewer here. It says pipeline browser. When you put modules in or data in, you'll get a little pipeline, which isn't that easy to understand when you've got a complex pipeline. And then for each module that goes in, when you highlight it in the pipeline browser, you get the module settings, so the properties of the module, so you could change an ISO surface or contour value, and you'll get information about the data as it goes in and out. And I've got another one over here, and these are your menu toolbars at the top as well. So we'll talk a little bit about them. So these are the common functions. So this redo undo button is there. We can see the apply there. This is the pipeline. We can see we've got a few objects in the pipeline. We've got a little eye that means that we can see the product of that module in the viewer. Load data. This is in your crib sheet, so it's not, I'm just doing very quick. So we can see this little blue line that tells us that this render viewer is active, and these buttons here will allow you to create multiple views of your data using different parts of the pipeline. So the one with the blue line around it is the one that's active at that time. And you'll get to understand these as you go. And then, so the blue areas on this show you the interactions which are on the CPU or on your desktop computer, whereas the ones in green are the graphics card. So the do undo buttons which are here, they only relate to the stuff that happens on your CPU, not on your graphics card. And that's another thing that often confuses people. They feel they're not getting consistency out of the user interface. And then the green area is everything that happens on your graphics card, which typically will happen a lot faster than anything that happens on your CPU. This is the point where I was going to suggest that we go to start some exercises. People do struggle when starting. They forget to press the button that says apply. They press undo and they expect things to undo that have happened on the graphics card. And the other thing that they could get confused with, the data is load data. The state is actually saving an application with data in it. So those are the things that people typically struggle with. So have a go and see if you have any problems with that. I'm here, Molly's here, Jonathan's here. We can all help you if you have problems. You can share your screen or we can share our screens to show you what's going on. So I can see one question here. I need to go back through. So the original, it depends which version of ParaView you've got. The original version of this course was developed for ParaView 5.4, 5.6, and I've updated it for this course to 5.10, which is the latest one out. And it's not a major version change, but there are some subtle changes.